Today we're going to have an interesting discussion about higher order elements and how they're used in CFD and what Tecplot is doing to make visualization of higher order elements possible. Our presenters today are myself, Scott Fowler. I'm the product manager of Tecplot, and Dr. Scott Imlay. Scott Imlay has been doing quite a bit of research for us on higher order elements, and with the goal of understanding what visualization packages need to do to bring this capability to you, and also with a goal of actually delivering this in the Tecplot product in the near future. So we'll talk a little bit about our timeline today.
Sure. So I want to start with just a review of higher order elements, what they are and why they're used in CFD, and then move on to the post-processing challenges, the visualization challenges. Talk about our research on the subject, and then our roadmap. Actually, Scott will probably take over for that roadmap for higher order elements in Tecplot 360. So higher order elements, well, most finite element methods assume linear variation of the solution along the edges of the element. So those are the standard linear finite elements. Higher order elements assume a nonlinear distribution across the element. Usually it's a polynomial of quadratic or higher order. Sometimes the element geometry is curved. Not always, but frequently. And the solver has better than second order accuracy. Here are some examples of, in this particular case, they're Lagrangian elements, and they have additional nodes. The black nodes would be the standard nodes you would see in a prism and a pyramid for a linear element, but the additional nodes, the red and the blue nodes, are edge-centered, face-centered, and there you can also have other nodes distributed throughout the cell for even higher order elements. Why are these used in CFD? Well, the main reason is you can get better accuracy or less cost for certain problems, in particular for unsteady flows and for vortical flows, those flows containing vortices. So the image on the right is an example of both. This is a wind turbine simulation. It's unsteady because the turbine the wind turbine is rotating relative to the pylon, and it is shedding a vortex off the tip of the wind turbine, as well as shedding vortices off of the pylon. And these vortices interact in a complex fashion. And so that's why you can see all these little vortices being formed by that interaction. Another example, problem where higher order elements are very cost effective is the aeroacoustics. These cases where you have these small pressure waves are often damped, heavily damped by the standard second order methods. But with the higher order methods, they don't get as highly damped as they would with the second order methods. So the lower right image is an example of what it should look like in this case. So this is a nozzle case, and you have pressure waves coming out of the nozzle and propagating downstream. Upper case is an example of what happens when you do make a common assumption in visualizing these results. And that common assumption is, well, we'll just throw out the nodes for the higher order elements and use only those black nodes you saw in that previous image of nodes. In that case, you get a result, and if you just visualize that with a standard scheme, the linear, for the linear elements, you get a result that doesn't look at all like the actual solution. You can see it's really not showing the waves well at all. So this is one of the motivations for why we are doing higher order element visualization. Another is, well, this is an example from CFD 2030. This is a NASA document. And so just to read it real quickly, higher order methods will likely increase in utilization during this time frame, although currently the ability to visualize results from higher order simulations is highly inadequate. So we're trying to address that. What are the challenges to visualizing higher order elements? Well, first of all, you have to be able to read the data from common file formats. CGNS, VTU, there are some others. And so you can't read it, you can't visualize it. And then you need to modify the internal data structures of your visualization code, Tecplot 360 in this case. It needs to be performant. So it needs to perform well without excessive subdivision. And most algorithms currently only work with linear elements. So algorithms for generating contour slices, isosurface, etc., assume that the extrema of the solution is at the corner nodes, which is true for linear elements, but it is not true for nonlinear elements. And so that really causes problems with those algorithms. And so we need to modify them substantially to work with the nonlinear elements. And then streamlines, streak lines, and particle paths need to interpolate using the new higher order basis functions. And finally, element edges and surfaces and mesh and shaded surfaces may need to be curved. They're not always curved, but you need to be able to show that if they are. This is an example of a basis function. So basically, you have your solution across the element as a function of the XYZ coordinates is a linear combination of the basis functions phi, which are also evaluated XYZ. And if the coefficients of the on those basis functions CI, if they are actually equal to the solution at the nodes UI, then the phi are the nodal Lagrangian basis functions. So basically, if you have a nodal basis function, what it means is that that basis function is 0 at all the nodes other than the current node I, and it's 1 at node I. So that's another way of looking at that. In all but pyramids, the phi are polynomials in X, Y, Z. So, but for pyramids, they are rational polynomials. And that's because the pyramid needs to match up appropriately along the triangular surfaces with tetrahedra, for instance. And you can't do that if you're just assuming a straight polynomial in the pyramid basis functions. So let's look at some algorithms for higher order isosurfaces. The goal is to visualize the higher order isosurface using existing algorithms for linear elements. So we have Tecplot has all these existing algorithms to work with linear elements. And so we want to be able to take advantage of those. And we use a subdivision technique, which creates a set of linear elements that represent the variation of the solution across the nonlinear elements. So we take that nonlinear element and subdivide it into a bunch of linear elements that are representative of the variation across the nonlinear element. And we repeat that subdivision until the desired accuracy is reached. And again, we're treating these smallest sub-elements as linear elements. Now, in the process of doing this, we will be creating new nodes. And we, at those new nodes, need to interpolate using the higher order basis function to get the solution at those nodes. Tecplot 360 will then use selective subdivision to reduce RAM and CPU cost. So what that means is we subdivide only those cells that may contain the isosurface, and then we discard the unneeded subelements as the subdivision progresses. And I'll show you some results about how much that saves us. I mean, it can be orders of magnitude fewer sub-elements. And here's some examples of the subdivision. This is the brick subdivision. So it's a 27-node hexahedra or brick, and it's subdivided into 8 sub-hexahedra. And then you can do additional subdivision by adding nodes on the edges of the sub-hexahedra and interpolating to the new nodes using the original hexa 27 quadratic basis function. Similar if it's cubic or quartic, same idea. Tetrahedra, the quadratic tetrahedra is subdivided into 8 subtetrahedra. As you can see on the right, additional subdivision again is created by adding nodes on the edges of these subtetrahedra and doing the interpolation with the higher order basis function. Now with the prism, it's a little different. So we started bricks went to bricks and tetrahedra went to tetrahedra. Prisms actually go to tetrahedra in our subdivision. So you can see it could be subdivided on the upper right into 8 prisms, subprisms, but then we actually take the extra step and we subdivide each of those subprisms into 3 subtets. So each quadratic prism is subdivided into 24 tets. And then on each subsequent level of subdivision, those tets can be further subdivided into 8 tets, just like it did for the quadratic tet. And interpolate to the new nodes using the prism 18 quadratic basis function and repeat as necessary. And likewise for the pyramid. So pyramid is subdivided into 16 tets for the original pyramid subdivision, and those are subdivided as before. So that's the basic idea. Those subtets then, as those that are selectively kept, are then used to do to create the isosurface using our standard algorithms within Tecplot. So this is an example for a prism. It's a curved prism. This is an isosurface of a distance from a point. So isosurface of a distance from a point should be a sphere. And in fact, it is a sphere, with a little bit of error. In this case, we use only 2,353 subtets, whereas if we had not been selective in our subdivision, we would have used more than 600,000, close to 700,000 subtets. So it's more than 2 orders of magnitude improvement in memory usage, and a comparable improvement in performance. Likewise for the pyramid, in this case, you can actually see the resulting subtets that are selectively retained. Same isosurface. In this case, it keeps 3,800 subtets, whereas if we had not been selective, we would have had 1.3 million subtets. So again, more than 2 orders of magnitude reduction in the amount of memory. So let's apply this to a real problem. This is a NASA Common Research Model in high lift configuration. This is some data we got from Z.J. Wang. He produced it with his HO music code. It's over 1 million quadratic elements, a mixture of tets, pyramids, and prisms. It's majority tets, strong minority of prisms, and then just a few pyramids to essentially glue the quad faces of the pyramids into some tets as necessary. And this is an isosurface of density at 1.95. So this is actually a compressible flow. The top is what you get if you just throw away the higher order nodes. The bottom is what you get with 2 levels of subdivision. So you can see it gives you a much better view of the details of that vortex coming off the fence on the nacelle, as well as the vortices coming off the end of the slat. Now in this case, the selective subdivision uses only 1.5 million subtets, whereas without the selective subdivision, we would have 113 million subtets. So you can see if we were doing two levels of subdivision, and this is a fairly coarse grid with 1 million quadratic cells, but if we had a finer grid, say 20 million, we would easily be getting into the billions of subtets if we were not doing selective subdivision. So it's a big advantage.
Hey, Scott, before we move on to this next slide, there are a couple of questions that have come in that I think are pertinent to answer right now. One question is about the difference in order between the grid and the solution. So we have a question, well, what if I have a linear element, but the solution on that element is higher order? What have we done in that regard?
Sure. Now we assume at this point that the elements are isoparametric, which means that the grid varies in the same way as the using the same quadratic functions in this case as the solution, but that isn't required as the person asking the question implies. And in fact, we don't do anything special in that case, but you can certainly specify the value of x, y, z at those extra nodes, so you get the same, you get a linear element. I mean, it'll still have the extra nodes, but it will be linear. And that's what I would have those people do at this point. In the long run, there would be some advantage to actually treat x, y, z differently, so you wouldn't have to specify the extra coordinates. But some memory advantage, but we're not doing that at this point. We will look at that in the future.
Right. Okay. So in the research code that we've done, we're assuming it's isoparametric cells.
Yeah, but again, a linear element, a linear geometry is a subset of an isoparametric cell. So you can still do it. It's just a little extra memory than would be required otherwise.
Yeah, and then this whole conversation was focused on isosurfaces. How is this different, if at all, for slices?
Oh, good question. A slice is actually an isosurface. I mean, it's an isosurface of a coordinate variable, or some linear combination of coordinate variables if you're looking at an arbitrary slice. So yeah, so it's the same algorithm. It's just instead of looking at density, in this case, you'd be looking at, say, the y variable at a specific value, and it would create a slice at that location. So actually in Tecplot, for some time, we've used the same algorithm for slices that we use for isosurfaces under the hood. I mean, obviously the interface is different, and that'll be the case as well once we implement this into the core of Tecplot 360. You'll be doing slices using the slice interface, but it'll go to the isosurface algorithm underneath, under the hood, to generate the slice. So this is just showing that we can also subdivide the surfaces to get a better representation of curved surfaces. And this is an isoparametric surface grid, quadratic triangles for, I think it's an Honor M6 wing leading edge. And so you can see that we've done 3 levels of subdivision in this case, and it actually nicely shows the curved leading edge. So talk about ongoing research. One of the things we're doing is all along we've been reading the quadratic data from CGNS files. We're now actually adding support for cubic elements into the CGNS files, so we'll be able to read up through P3 in the short term, very, very soon. Stream trace research. So we don't use subdivision to linear cells to produce the stream traces. That's just that's a rather expensive way to do your interpolation. So we've actually modified our interpolation that we use at each step of the stream trace to use the higher order basis functions directly. And we're actually looking at using the local coordinates, which are RST, I'm calling them in this case, instead of global coordinates X, Y, Z. And there's a couple of reasons for that. So I want to do a slide on that. So the differences between X, Y, Z and RST stream traces. So the current algorithm incrementally adds an XYZ point to the stream trace based on the local velocity. It's a little more complicated than this, but you can just think of it as you're at a point, you get the velocity and you move in the direction of the velocity a little bit, and then you have a new point and so on. We actually do a rung and cut type approach, but it's basically the idea. So at the new point, you interpolate to get the new UVW from the new XYZ value. And you have to do that every time you add a point to the velocity. And actually you have to do it a couple times with the rung and cut method. With isoparametric higher order elements, this requires an iteration to compute the local coordinates RST from the global coordinates XYZ on each step. So it's a Newton iteration, and each iteration within that requires the solution of a 3x3 linear system of equations. So you have to, do 10 to 20 of those solutions for each interpolation in order to get a good estimate of RST from the XYZ value. And then you turn around and use RST to compute your new UVW velocity. An alternative approach that we're studying is to use and to actually increment the stream trace in the local coordinates, the RST coordinates, and instead of XYZ coordinates. Now, to do that, you need to compute RST coordinates velocity components, which I'm calling U prime, V prime, W prime here. So you compute those from UVW both by solving a 3x3 linear system equation. It's the same 3x3 that we solve, 10 or 20 times to do the interpolation in the previous algorithm, but we only do it once here. And then once you're there, it's relatively inexpensive to compute XYZ from our RST. It's just a basis function evaluation. This is much cheaper on each step than doing it in XYZ coordinates. Now, this is a case where if we actually had linear geometry, that benefit would go away because it's primarily a problem with curved geometries. But we're assuming that nonlinear curved geometries. So why would you want to do this? Well, and what are the advantages? One of the advantages of integration in RST coordinates is that the coordinates are very simple within the cell. They go, just looking at this hex, for example, it's a little more complicated for tets, et cetera, but not much. So they go from -1 to 1 for the hex in R and the S and the T coordinates. So determining that a point is in the cell is very easy. If it's 1.01, it's outside the cell. If it's 0.99, it's inside the cell, for example. And it's cheaper per step because it doesn't require an expensive iteration. So it's an order of magnitude fewer solutions of that linear system. Disadvantages, well, another advantage I would like to say before I go to the disadvantages is that if you have an extremely thin element like the one you see down in the bottom right, so this is a common type of element you'll see near the wall for no-slip walls. So it could be, order 1 dimension in the long side, but in the short, if you look at the depth of that element, it might be 10 to the minus 6th. And so that makes it much harder to select a step size. So, you know, because if you select 0.1, well, that would be great for, in this case, something close to the x direction, but it would be terrible for if the stream trace were going in the z direction. So you have to be much more careful with this, with the step size in XYZ than you do with the step size in RST. Anyway, disadvantages. The big disadvantage is the transition from cell to cell is more complicated because the RST coordinates don't match up. You know, you're going from one in S on one cell to -1 in T on the next cell or something like that. And so you need to be a little more clever. It's not really that hard, but you do have to be a little more clever. The other one, from our perspective, it would require some significant changes to the stream trace code within Tecplot 360. So here's some results. This is just a vortex with flow down it. So it's a rotating flow. It should be a helix on the left side. And you can see there that both the red and the black are pretty much a helix. If you look down it from the top, which you do on the right side, down the z-axis, it should be a perfect circle. And the black one is the standard our XYZ integration, and you can see it's not quite a perfect circle, whereas the RST integration is. So it does have some advantages in this particular case for accuracy to do RST integration. Future development. Did you want to handle this, Scott, or?
Yeah, sure. I'll jump in here. Before I get into this slide, I do have another clarification question on how we treat the geometrical basis functions versus the solution basis. So this again goes back to that idea of the what we were talking about, isoparametric and potentially linear geometry. It says, do we assume that both the solution and geometrical basis functions are identical? And how does Tecplot know what solution basis functions to use?
Okay, the answer to the first question is at this point, yes. We assume they're identical. And the way around if your CFD code does not have identical basis functions for the geometry and the solution, well, then you need to choose one of them, probably the one that is the highest order highest order polynomial, and then you would interpolate the other to that to get that to that basis function. So how does Tecplot know what the basis functions are? Well, you need to tell it. So for instance, if you're reading a CGNS file, it will have the element type in there. It will have, for instance, that this is a tetra 10. This section of this zone is a tetra 10 element, and so that then is stored in the data structures, and Tecplot will take advantage of that.
So for future development, I may be getting a little bit ahead of ourselves because we do have a release coming out in October, so 2021 R2. But I'm telling you what's going to happen next year in 2022. So we are putting a stake in the ground, and we're saying we are going to support higher order elements to a certain extent in our first release of next year. So that will include a lot of what you saw Scott present on today. So higher order elements will be supported for isosurfaces, slices, and curved message. So that was really the first half of Scott's conversation. We're going to be focusing on compatibility with the CGNS file format. They seem to be about as far along as anybody for higher order element support within the data files. We're going to be focusing on that file format. So if you are in charge of a CFD code that is exporting data files, CGNS we think is the furthest along as far as HOE support goes. We're going to be assuming Lagrangian elements up to P3, and then other features within Tecplot are going to initially ignore the additional nodes. So we're going to be, some of our algorithms are going to continue to treat the higher order elements as linear. So there are going to be some small downsides there. Scott, could you clarify what some of those other items that will be ignoring the additional nodes would be within Tecplot?
Sure. Well, initially, for instance, the derivative calculations within Tecplot will still be ignoring the higher order nodes, which is, so if you're, for instance, if you want to look at Q, it's probably best that you would compute Q or vorticity within your CFD code and export that as a variable. At this point, we will be adding support for higher order elements there in the future. I mean, that's the big thing I can think of off the top of my head. Do you have any others that you're...
I can't think of any others. It's just the variable calculations, the derivatives. And then beyond that initial release in 2022, we'll start looking into the stream trace code that Scott mentioned, using the RST technique, and then supporting other file formats. I know VTK's VTU file format supports higher order elements, and we'll be considering adding higher order element support to the Tecplot file formats themselves. And then just adding features as the higher order element community needs it. We had a really interesting conversation with one of our development partners on the research code that Scott has been doing, and he mentioned that he really feels like the missing piece to make high order elements commercially available is visualization. And so that's really our goal, to help the people who have been working hard on the CFD codes. I know we have friends over in the pre-processing, making high order meshes. We want to help this community move forward and be able to make higher order elements part of your workflow. So that's what we're working on, and we're looking for partners. So Scott, if you advance to the next slide, partners needed. So any of you that are on the call today, if you have an HOE code that you're using and you want to test out any of this research work that we've been doing, Scott and I want to hear from you. We have a pretty good set of people that we've been talking with already, but as we get further and further down our development path, we're going to need more and more people to test this out and give us feedback. So we definitely appreciate you getting a hold of us. So those of you who have given us your attention and signed in today, we really appreciate it.
Yes, thank you. It was a pleasure to have you here.
Appreciate your time. Thank you very much.